Okay, so let's jump right into it then. Here is our equation of motion with all in its glory, with gradient of pressure, the potential we defined, including gravitational potential and the centrifugal force, and of course the Coriolis equals friction. So if Rossby number is small, let's say mid-latitude atmosphere or the ocean, R0 is order 0.1 for mid-latitude atmosphere, and we'll see that for the ocean it's much smaller. Then we can drop the acceleration term and the vertical hydrostatic balance, which also is gone. So then we can just balance the Coriolis with the gradient of pressure. Okay, so obviously because in the vertical gradient of pressure is balanced by Gz, right? We have hydrostatic. So Fz hat cross U plus 1 over rho grad P equals 0. This is the famous geostrophic balance. I alluded to it before in several podcasts. What we're doing here is basically balancing the gradient of pressure with Coriolis. Okay, so this is the famous geostrophic balance. We can just cross this equation with another z hat. So z hat cross u is minus u with our vector calculus that you can look up. The appendix of the book provides some of the basic vector calculus, by the way. In case you've forgotten, you can revise it. So this equation then basically becomes minus u plus z hat cross 1 over rho grad P equals 0. And u in this case is in geostrophic balance, so you can write it as ug. Because of the minus, we can move this to the other side. So we have divided by f, and we got 1 over f rho z hat cross grad P. Okay, so we haven't said anything about rho. Obviously, we have said before that it's an inconvenient variable because it's not easy to measure, and we will end up obviously using our ideal gas law to express it in terms of temperature soon enough. Okay, so this is now the geostrophic velocity vector related to the gradient of pressure. Writing it as components, then ug, the zonal geostrophic velocity, and vg, the meridional geostrophic velocity, could be winds or ocean currents, are equal to minus 1 over f rho dp dy and 1 over f rho dp dx. See the relation here. Because Coriolis pushes to the right, x and y are related in this way. So dp dy, meridional pressure gradient, is going to give you zonal geostrophic velocity, and zonal pressure gradient is going to give you a meridional geostrophic velocity. Okay, this is a very powerful constraint on large scale flows. We already had one powerful constraint, hydrostatic balance, we have carried for a while now. Now we're going to add geostrophic balance to that. Obviously near the equator f goes to 0, so this is not a very strong constraint near the equator, although in the ocean you can find some zonal geostrophic balance with some approximations. Okay, so remember this is frictionless, right? So what does it mean net? So you have a flow around high pressure. So if there is high pressure at the center, low pressure all around, flow will want to go from high pressure to low pressure. If you're in the northern hemisphere, the flow is going to be tilted to the right, so flow would be in this direction, so Coriolis would push it in that way. Pressure gradient is in this direction, so minus 1 over rho grad P is in this direction, and Coriolis is exactly in the opposite direction, giving you this geostrophically balanced flow. But what is amazing here is that these are constant pressure lines, so you're going to have flow, instead of down the pressure gradient, you're going to have it parallel to isobars or constant pressure lines. Okay, the same thing when you look at a flow around low pressure center. You have low in the middle, high all around, so flow is going to be from high outside towards the low inside, and you can add Coriolis to get the rightward deflection here, and you have now the pressure gradient going inward and Coriolis outward balancing. You can do this very simply to get your clockwise flow around the high, which we will call an anticyclone in the northern hemisphere, and a counterclockwise flow around a low pressure center in the northern hemisphere, which we call cyclonic flow. So all your tornadoes and hurricanes, cyclones, typhoons are all cyclonic flows, right? That's the basic idea of geostrophic balance. You can see how the counterclockwise flow here would work. So you draw flow going from higher pressure into the lower pressure, you apply Coriolis, you do that all around, and you end up with a counterclockwise flow, and similarly he will end up with a clockwise flow here. So looks disarmingly simple, and it is, and it has many consequences as we will see. So the geostrophic balance comes about when R0 is very small, which means acceleration term is dominated by the Coriolis term. Okay.